Oh, just right here. Right there. All right, please turn in your take-home quiz.
Number 4. We're trying to do that out earlier. It's a very long process, right? Pretty much, or is there
Doesn't have to be. I'm going to cover some of this today.
All right.
Yeah, no, it's all right. Just right there. I've seen one around here. I don't know. I guess someone has it. There used to be one that's no longer around. Just right there. Yep. Is your bonus? Did you do the bonus? Is it separated though? Okay, yeah. As long as it's separated, that's fine. All right. Has everyone turned in their quiz? That's going to turn it in? It's right up here. All right, so what kind of issues are you all running into? Anything you want to discuss about the take-home quizzes? The fourth one with the limits? Okay, we can talk about that. But I mean, as far as like the big picture of things, are you all starting to get an idea of what I'm asking you to do? Yes? That it's not going to be just like a cookie cutter problem from like what we did in class. It's going to require that you go beyond that. Yes? Okay. I have another quiz for you today, but we'll hand that out later. I do want to address this because our calendar, we're supposed to cover today, what is it, 11/7? No, 10, where is it? 10/7, we had already started it, right? So because of that, I'm going to take a little time to talk about this quiz that you just turned in. So any last call? Anyone else? Okay, I won't accept it after now. So on number 4, you're given a vector function t cubed plus t over square root 4t to the 6th minus 3t cubed plus t. And then the next component is t to the 1 over t. And then the last one is t natural log 1 minus e over t. And you're asked to find the limit as t goes to infinity. All right, so the first one, the first component function, what I can do is not apply L'Hopital's rule, because if you do apply L'Hopital's rule on the first one, it's a disaster, right? Because the derivatives become pretty ugly. So we actually use a method that we used in calculus before we learned L'Hopital's rule, and we were taking limits in the very beginning in Cal 1. And that was to try and kill off the highest power of t that we see. In other words, I want to take this t to the 6th and make it go away and just become a 1, or make it a 4, okay? So what I'm going to have to do is divide by t to the 6th. But whatever I do to the bottom, I have to do to the top. So what you have to realize here is that the only way to get a t to the 6th inside a square root is to start off by multiplying outside the root by 1 over t cubed. If you multiply by 1 over t cubed and then force it into the root, it gets squared on its way in, and then it'll be a 1 over t to the 6th. So here's the part I'm coming in with. 1 over t cubed on top, 1 over t cubed on the bottom. I'm going to multiply that times what was there. So here's my t cubed plus t. On the bottom is that root of all that stuff, right? So when this goes in, it becomes 1 over t to the 6th. Is that clear? That's like the key to the entire problem, I guess. On the top, when I distribute, I get a 1, and then what? Plus What is it on top? Okay, 1 plus 1 over t squared, because it's really t over t cubed, so it's 1 over t squared. On the bottom, when this thing goes in and becomes 1 over t to the 6th, it turns this first piece into a 4, right? And then minus, what? 3 over t cubed, and then plus 1 over t to the 5th. That makes sense? Dividing each of these by t to the 6th. Now let t go to infinity, and this one vanishes to 0, this one vanishes to 0, this one vanishes to 0, and all you're left with is 1 over the square root of 4, which is 1/2. So the limit's 1/2. How did I get what part of it? I divided this by 1 over, well, I divided by t to the 6th. Because of the t cubed, 1 over t cubed goes in the root, it gets squared on its way in. Just like if you have something squared under a root, when you take it out, you take the square root of it. If you want to put it back in, you have to square it on its way in. So if you take 1 over t cubed and square it, that's 1 over t cubed times 1 over t cubed. That's 1 over t to the 6th, isn't it? And that, so dividing this by t to the 6th, you get 4. Dividing this by t to the 6th, you get this, and then t to the 6th. Make sense? Yay, nay? Yeah. Okay. So that's how that one worked, okay? I think I said in class, like there's a section in the book on L'Hopital that you can go back and look at. No? You didn't see? Right before they introduced L'Hopital's rule, they did a problem similar to this, where they came in, they divided everything by t squared, or x squared. Or if you're just coming in, you got to turn in what you have if you have it. Okay, next one was limit t goes to infinity, t to the 1 over t. Now, I didn't talk about this in the previous problem, like what was the problem? You know, like why did we have to do all that? In the previous problem, we had infinity over infinity, right? And that's an indeterminate form, and so we have to do something about it. Here, what we're getting is we get a form where the base wants to become infinite, but the exponent is headed to where? 0. 0 to the infinity is an indeterminate form. The base wants to get big, the exponent wants to be 0. Anything to the 0 should be 1, right? So it's kind of like who wins. So we have to do something. The way to do this, see if this rings a bell. Rewrite the problem, calling our limit y. So I want to know what y is, don't I? And now I take the natural log on both sides of this equation. So I take the natural log, and whenever you take a natural log, you can pass the natural log through the limit. Why in the world would I come in with the natural log here? Because there's a property of logs that says if I have log of something to a power, I can take the power out front, can't I? So that power is going to drop out in front. So what I get is natural log y equals limit as t goes to infinity of natural log t over t. So what did I do there? That 1 over t out in front really means there's just a t on the bottom, right? And now let me do t go to infinity now. When I do that, I get natural log of infinity, which is infinity over infinity on the bottom. Now that's still an indeterminate form, but now I can use L'Hopital's rule. Right? L'Hopital you can only use when you have infinity over infinity or 0 over 0. So I apply L'Hopital's rule now. You can use an L or an H. That's the way I do it. Limit t goes to 0, infinity. The derivative of natural log t is 1 over t. Derivative of 1 on the bottom is, the derivative of t on the bottom is 1. And now let t go to infinity here, and we get what? 1 over infinity is 0. 0 over 1 is 0. So we have 0. So natural log of y must be 0. And now if I take e on both sides, I can get rid of the natural log. So e to that and e to that. So that means y is what? E to the 0? 1. So that should have gone to 1. Questions? the last one, limit t goes to infinity. What was the last one? Oh, t natural log. Okay, if you let t go to infinity, you get infinity right here times, let's see, e over infinity is going to go to 0. 1 minus 0 is 1, right? Natural log of 1 is 0. So you're getting infinity times 0. This is also an indeterminate form, so we have to do something here. So the trick here is to try and turn it into a fraction. So we can use L'Hopital, right? Something over something. So what I can do is I can leave the natural log alone up top. Actually, I'm going to write this like this. That's the same thing, right? This is this. And then what I'm going to do is I'm going to bring the t that was up in front here, I'm going to bring that down on the bottom, but when I bring it on the bottom, I have to write it as a 1 over t. Isn't t on the top the same as 1 over t on the bottom? And now you have two fractions, don't you? Or you have a fraction. You have this, numerator, and then you have denominator. So you take L'Hopital rule now, and you'll get something. Let's see. So by L'Hopital's rule, I need to take the limit as t goes to infinity. The derivative of the top. So the derivative natural log of something is 1 over itself. No. You all agree that's the derivative of natural log of something. And then we have times the derivative of what's in here. So what's the derivative of what's in here? Well, derivative of 1 is 0 minus, let's see, e is a constant. Derivative of t to the negative 1. Negative 1 comes down, right? So that makes it e t to the negative 2. And then all of this over the derivative of the bottom. Right? Derivative of this is negative 1 over t squared, or can I just put negative t to the negative 2? Like that? Same thing. And this right here and this right here are the exact same thing, aren't they? So they cancel out. And now let t go to infinity again. So maybe I'll rewrite it one more time. This is the limit. T goes to infinity. Let's see. We had a negative down here, didn't we? And we have an e up here, so I'm going to put negative e over 1 minus e, or I'll do it this way, e over t. I rewrote this e times t to the negative 1 as e over t again to help me see that when I let t go to infinity, this is going to become what? 0. So 1 minus 0 is 1. So your answer is negative e. That problem called on just about every possible technique for finding weird limits from Cal 1, right? Yeah. Well, the thing is, what I'm trying to help you do is bring all this stuff back up to the surface, because, you know, going and transferring over to like an engineering class, you know, this may pop up. You may have limits that you haven't done in a long time, so you need to make sure you know, have some familiarity with them. You know, it can't be like, oh, well, I passed that class, I don't remember, it doesn't matter anymore. It's going to matter, so. All right? Okay, anything else on this take-home quiz? The first three, the visualizing of things. Sent that one? Is that the one you're talking about? Parallel. Okay, and then on the one with the center, the quadratic surface, what was the issue on that one? Just finding the center, or how to do the whole? So complete the square. Did you do that? The center would be, you should have like x minus x naught, and then the other parenthesis y minus y naught, and then z minus z naught.
Okay, so if it's like 3x minus a number, would it be?
Let's say you would have had this. Okay, the center of this one, well, I'm not done, but this center of this one would have been 2, negative 5, and then whatever. I think they were fraction. It was a fraction, right?
Right.
Some of them were fractions.
Like one of them was like 3x. Inside that square thing, it was like 3x.
Inside here,
yeah.
You can't have that. You always have to factor out. You always have to, if you're going to complete the square, you always have to have a leading coefficient of 1. So you've got to factor that out first. I'd have to look at your work to see, but okay. Let me start with this one. So I'm not going to do this whole problem. All right. Well, you know what I can do is I can bring up the answer, I think. Let's see. This is it right here. Basically, what we want is the shortest distance between a point and a line, right? The point is the center of the quadratic surface. The line is the intersection of the two planes, right? That's what it gives you. It says find the shortest distance between the center of the quadratic surface to the line of intersection of two planes. So first thing, let's find the point, which is the center of the quadratic surface. So here's my quadratic surface. I complete the square. I get negative 3 1/2, negative 3 halves. That's the center. Okay, so I have a point sitting in space. Quadratic surface doesn't play any other role in this problem at all. It's gone. Forget it. You just have a point. Now you need the line of intersection of two planes. Well, when you have two planes, if you want to find that line of intersection, you first need a point on the line. So to find the point, I just let z be 0 and I figure out what x and y had to be. Now you could have done anything. You could have done, any point. It does not have to be this one. All right? But you need a point. And then you need a direction of your line. But we talked about in class that if you have two planes that intersect, the direction will be what? How can you get a direction of that line if you have two planes? Cross product of the two normal vectors of the planes. So I take the two planes, I take their normal vectors, I cross them, and that's my new direction. So now I have a line and I have a point. And I want the shortest distance between a line and a point. And so we did an example like that in class. I gave you a point, I gave you a line, you find the shortest distance. You just applied a formula. This was it right here. Yes? Yes. Yes, I'm going to do that now. Okay? So that was this one. Does that answer your kind of question on that? All right. Okay, on the other one, we're given, it says find the equation of the line through a point, they give you the point, which is both parallel to a plane and perpendicular to another line. And the people who did come to me for help with this, I don't know, it was easier to just look at it in this respect. So let me do it this way. So let's just say, to try and help you visualize this. Okay, just like that. Okay, so let's just say I gave you a point, right? Here's a point in space. Then you need a line that goes through that point, right? Your line has to go through that point. So it could be any of these lines, right? In any way. So there's an infinite number of answers. But you have to be parallel to a plane that I give you. So let's say that's the plane, right? Right over there. So to be parallel, I'll move a little closer so we can see this. Do you agree that this line is parallel to that plane? Yes. Now, but it can be any of these lines, can't it? All of these lines are parallel? Yes? All right, so now I need to figure out which of these it is. So let's just keep it like this. I'll move out here a little bit. Remember, it can be any of these, right? But there's a line over here that I have to be perpendicular to also. So are these two perpendicular? Do they look perpendicular to you? No? Okay, but I can spin it around, but I have to stay parallel to that plane. Eventually, I don't know where it is. I'm thinking it's right around here. Because if I move these together, you see how they're perpendicular there? Okay. So now let's get back to the main idea. How do I find the direction of this line? I have to be parallel to this plane, which means the direction of this line has to be what? Scale, but this one doesn't have a direction. Right? The plane doesn't. What do we know about a plane? What's the only real good information we have about a plane? It's normal vector, right? So how is the direction of this line related to that normal vector? They're orthogonal, right? So my direction has to be orthogonal to this, normal. And then this other line has a direction, and I'm supposed to be perpendicular, which means this direction has to be orthogonal to this also. So that means you're trying to find a vector that's orthogonal to two other vectors. How do you do that? This is one of the big points. That's correct. So you could say that the dot product with those two has to be 0, but look, think about it. Back up. You are trying to find a vector that's orthogonal to two others, right? When you have two vectors and you take the cross product of two vectors, that always gives you a vector that's orthogonal to those two vectors, right? So why not take the normal and the normal of the plane and the direction of that line and cross the two? That answer is guaranteed to be orthogonal to both, which satisfies both conditions simultaneously. Does that make sense? So that's what I did here. So must be parallel. You must be parallel to this plane, right? Which means it's orthogonal to its normal vector. Also, it must be orthogonal to this line, which means V must be orthogonal to the direction vector of that line. But the cross product of those two vectors is a vector orthogonal to both, thus a great candidate for V. Let V be the cross product. We had the point. Here's our direction. We're done. I will also point out, if I went back, okay, like I did the solutions to this problem actually years ago, probably about 2 or 3 years ago, and I'm coming back to my answers right now. Was it pretty easy to see from my work what I did? That's part of, you know what I'm saying? Like I'm explaining each step of what I'm doing and the rationale behind it. That's something as an engineer, as whatever your major is here, we're all in some sort of field where we have to communicate our thoughts and we need to get good at it. It's good practice to write down your answers in a logical, laid out manner that you could go back and read it a semester from now or a year from now or 6 years from now and be able to make sense out of what you did. Does that make sense? Especially if you have to do something for a real job and you have to hand it over, you know, they're like, hey, we're going to build a bridge. I want you to come up with all this stuff. And then you go hand them, it's like, here's the answer. And they're like, well, where's your work? Well, it's all in here. Don't worry about that. There's the answer, you know. I mean, they're going to want to see the logic behind it, right? When you're checking it with your partner, you know, okay, yeah, you check this. You got to be able to communicate that. So that is a skill, and it takes time to develop that skill. In fact, we had a meeting, all the calculus faculty had a meeting this past Friday, and we were talking about how much we should be taking off for improper communication, for clarity not being there in Calculus 3 and Calculus 2. And we all have different opinions. I mean, I think it's something that you have to develop, but you have to work on it, okay? When I collect these assignments, I am looking at neatness, but I'm also looking at logical process. You know, can I make sense out of this? Can you make sense out of it later, you know? So work on that. I had an excellent student, I won't mention his name, last semester, but he was one of those students who was really smart, but it was like, I just know the answer. I can just do it, here it is, scribbled it down, just didn't really show anything. And I was taken off on everything, and he was all upset because, you know, it was right, but I was counting it wrong. And so I sat down, I gave him basically the same talk I'm giving you. And throughout the semester, he worked on it. And by the end of the semester, he was excellent at communicating his ideas. And he thanked me later. He's like, you know what, this is something I really need to do is slow down. And when I think it out and write it out, I understand it better also. So, all right. Make sense what I'm trying to get at? Okay. Any other questions on this? So you should get help, okay? You know, part of this is for you to work on your own and try and grind through these, but if you're completely hung out, just, I had no idea what to do with this, that's why you have my cell phone number. That's why you can text me. You know, I'm here to help. You just have to reach out or come to my office. All right, what's next? We're done with this. I have a handout for you. Oh. We will get to new material today, but I thought that this would be a good little exercise for us to look at. There's 19 problems here. These are in no way required problems, but I'm going to say that these are bonus problems that you can do to be turned in at our midterm. Okay? So do not make this the focus of your life, all right? These problems are not designed to take you away from the new material. But to me, this is a good summary of lines and planes and the types of problems you should be able to solve when it comes to lines and planes. So I want to read through these real quick, and since I'm recording this audio, you can go back and listen to it. I'm going to talk about little hints and things. Look at number 1. Find the vector equation of a line through 2 points. That was your quiz last class. Remember I gave you all that quiz? Everyone take out a sheet of paper. We had 2 points, find the vector equation of a line. I would expect everyone here could do that now. Okay, so there's all you have to do there. You already have a point. All you have to do from those 2 points is create what? Your V, right? Your direction, and then you're done. Okay, find the vector equation of the line segment. What's the only difference between 1 and 2? Domain restriction on T, okay? Number 3, find the vector equation of a line through a point and parallel to the line with parametric equations. Okay, so what does that mean? I need the vector equation of a line, which means I need what things? For the vector equation of a line, what do you need? A point and a direction, right? I already gave you the point, so all you need is a direction. You have to be parallel to another line, which means that, what? But I gave you a line, not a plane, right? Right? So how can I figure out what the direction of my line is going to be? Taking the direction of that line, right? And then I'm parallel to it. So just use the direction vector of that line. Okay. 5, find the vector equation of the line of intersection of these 2 planes. You had to do that in number 3, didn't you? Find the vector equation of the line between 2 planes. So you find a point of intersection, then you find its direction by crossing the normals, right? These slowly and steadily become a little more complicated. All right, find the vector equation of a plane through a point and perpendicular to some vector. So find the equation of this plane right here that goes through a point but is perpendicular to a vector. So here's a vector. I have to be perpendicular to this. So you think it through. All of these problems are very much connected to numbers 1, 2, and 3 on this test. In fact, there's probably problems 1, 2, and 3 probably appear in here somewhere in some fashion. And then you keep on going through this. You start to get to the bottom of this where you're trying to find the shortest distance between a point and a plane, a point and a line, shortest distance between 2 planes. Find the distance between 2 skew lines. That's a hard one. In fact, you know what? Let's take 19 off. Well, I mean, look at what it's saying is this. You have two lines that don't intersect. They're skewed, so they're not parallel, they're not orthogonal, they don't intersect. Find the shortest distance between them. You have to, you have to figure out the shortest distance between them. That's a little bit of a challenge. So don't get bogged down on that one is why I'm saying don't worry about it. So midterm, turn this in. Nice and neat in order. 1, number 2, number 3, number 4. And I'll give you bonus for it, okay? We'll probably use it maybe to replace one of your take-home tests, right? You know how you like, I'm giving you these quizzes. All of these problems will replace one of those. Yes? Right now there's not a plan to, but there's always that chance, yeah. It's a lot of your grade. I don't remember how much. I'm also giving you in-class quizzes. Those do not count the same as your take-homes, obviously, right? Like, so that quiz you had the other day in here that only 2 people got it right, that's not a 0 for like the equivalent of a take-home quiz. You don't want it to be, right? You don't want that to happen. Okay. So I will weight them appropriately so that it's fair to everyone. I just have to see how many I have at the end. I don't know. I don't know yet. Okay. Let's get back to where we left off last time. Where were we? It was this problem right here. I'm gonna kill some of these lights. A little too bright in here. Remember that one? Oh, that was a bonus problem. Did anyone do it? Anyone have that to turn in? I had asked to do the algebra to verify the domain of that. No? I'm only saying it because if you have it, please turn it in. Okay. All right, so in this semester, I don't want anyone saying, hey, how do I get an extra 2 points? I'm offering you bonus. If you don't do it, I can't do anything about it. All right, so we move on. 10.79. It's probably obvious to you that if somebody gives you a vector equation like this one, that when you graph it 3-dimensionally, if it's easy like this one, because this one's a line, that it's pretty easy to graph, right? But in general, they're not so easy to graph 3-dimensionally. So a lot of times we use a computer to graph them, and these are just some examples of some cool vector curves in 3-dimensional space. This is called a toroidal spiral. You know where it gets that name from? Toro, you know where this comes from? The torus. The torus is the fancy name for a donut, okay? It's a fancy name for a donut. And you take a donut and imagine a spiral wrapped around it. It's called a toroidal spiral. So I didn't include the vector function. I didn't put it in here, but I can go real quick to my code. This is it right here. That's the first component of the vector function. So it's 4 plus sine 20t times cosine t. The y component is this, and the z component is this. If you define your vector function like that, then it will draw your toroidal spiral. Okay? Another example, trefoil knot. Trefoil knot. This is a curve in 3-dimensional space that actually ties a knot on itself. So if you follow the path, it goes inside of itself and comes back outside. So I won't bring up the function for that one. Okay, so you can draw some really crazy curves with vector functions. Anybody know where the torus comes from? The donut? There's a class called topology that math majors will take, and it's based on this principle that if I were to take a sheet of paper, if I were to say I want this edge to become this edge, right? Basically put those two together, and then take this edge and paste it together with this edge, what would happen? So if I put these two together like this, right? It would do that. And then now you have to paste this edge and this edge together. So you wrap it around, and when you do that, you create the torus. Do y'all see that? So that's all in a class that you would take if you were a math major. Another one that you may have heard of is the Mobius strip, where all you do is you take this top edge and you map it to this edge, except that this corner goes to the opposite corner and this corner goes to the opposite corner. So you twist it once and then put it together. And when you do that, you get the Mobius strip, which is an example of a surface that only has one side. So you have your thumb and your index finger. If you follow your index finger around, you'll come to your thumb and keep going. You go back and you'll be at your index finger. And so it's this one-sided surface. If you take, if you go back to the donut again, and you map these two together like that, and then you put those two together, you get the donut. But if I do this edge to this edge, and then this edge to this edge, but cross it, like this corner down to this corner and this corner, if I do that, I get what's called a Klein bottle. Has anyone ever heard of a Klein bottle before? A Klein bottle, Mobius strip is an example of a surface with one side. The Klein bottle is an example of a volumeless solid with no volume. And it cannot be visualized in 3 dimensions. It can only be done in 4 dimensions. Look it up, Klein bottle. It's kind of an interesting concept. But all those are topology topics. So I know there's a few math people in here, and that was one of my favorite courses. Topology. It was really, really kind of cool. But at the end of the day, I spent like the better part of 2 years studying the difference between a coffee cup and a donut, you know, and it's like, really. But what you realize in math is that you develop these very specific branches of mathematics, and you develop all this structure around these basic principles, and then you realize that there's another problem in math that they've been trying to solve for a long, long time, and you actually stumble upon an easier way to solve it. In fact, maybe you find a way of solving something that hadn't been solved before. So these branches of math that seem very obscure and useless can actually turn out to be very beneficial. So that's why people continue to study them. All right, off topic. Let's get back. So we have the idea of a vector function, which is just a 3-dimensional curve, right? A curve in 3-dimensional space, or a curve in 2-dimensional space. But 3D is more interesting to us, right? All right, so if we have a curve moving through space where we imagine it's like a fly flying around the room, right? It has some path, then we can definitely talk about the derivative, which is the instantaneous rate of change, right? That's what it was in calculus. And fortunately for us, like the derivative of a vector function is just the derivative of its component. So you just take the derivative of each of the component functions. That's your derivative. So we don't have to do anything fancy. Now, you do have to remember how to take a derivative, though. So what is the geometric meaning of the derivative? When you take the derivative of a vector function, you create a new vector function. If I give you a value of t, then r prime of t is a vector, and that vector is tangent to the curve at the point on r of t. So I'm going to show you an example, but let's work through this first. Let's actually take this vector function and compute its derivative, and then let's find the derivative at pi over 2. Yes, dr, it's like dr dt, but r is the vector function r. So we have r of t in this problem is defined to be t sine t, t cosine t. What does this draw? Think about this for a second. If, oh wait, was this two-dimensional? Yes, we're in two-dimensional space, right? We're in two-dimensional space. Yeah, it's, remember, if this was like 4 sine t, 4 cosine t, it would draw a circle radius 4, wouldn't it? But what's happening is that the radius, the t, is actually varying with time. So when you start at t equals 0, what's your radius? 0. And then as t gets bigger, what happens to the radius? It starts getting bigger. So it starts trying to draw the circle with the radius getting bigger and bigger and bigger. So it should look something like this, right? It's trying to draw a circle, but as time goes on, it gets further and further away from the origin. So it looks kind of like a spiral, right? Okay, now let's take the derivative. So fortunately for us, all we do is take derivative of each component. What's the derivative of t sine t? What do you have to use there? Product rule. So you have sine t plus t cosine t. That's the derivative of the first component. What's the derivative of the second component? Cosine t minus t sine t. Everyone agree? So that's the derivative. It is a new vector function, right? It's a new vector function. I could graph it. It would look different than the original one. But I'm interested in knowing first, well, after finding the derivative, find the vector that's tangent to that to the original curve at t equals pi over 2. So that means I want to know what r prime of pi over 2 is. So plug pi over 2 in for everything. What's sine of pi over 2? 1 plus pi over 2 times what's cosine of pi over 2? 0. Cosine of pi over 2 is 0. Pi over 2 times sine of pi over 2, which is 1. So we get the vector what? 1 negative pi over 2. Agree? So if I were to just look at this vector real quick, 1 negative pi over 2 would mean to the right 1, down pi over 2. What's pi over 2? About 1 point something, a little bigger than 1 though, right? So this vector looks something like this. Do you agree? It goes to the right 1 and then down more than 1. Something like that? That's what the vector looks like. However, this vector should represent the tangent to our original curve. So remember that vector can slide around, right? So what we want now is the actual equation of the line that's tangent to our curve. I think now would be a good time to show you what's happening. Here's our original spiral, okay? Hold on. Oh, notice I had the sine and cosines flipped here, right? So it drew the circle, but because sine and cosine are flipped, it's drawing it counterclockwise instead of clockwise. I didn't notice that at first. So that's why it's drawing the circle counterclockwise. The radius is getting bigger, right? And we want to know at exactly a certain point in time, right? Do you see my tangent vector, my red one here? That's our derivative, okay? We want to go to exactly pi over 2, which is, yeah, I can just go in here and just put in pi over 2. Yes. Whoa. I don't know what happened there. There we go. Pi over 2. So at exactly pi over 2, here's my tangent vector, right? That matches up with what we got here, right? It looks kind of like that, doesn't it? Of course, it's been moved over, but that's what it is. And now I would like us to find the equation of the line, the vector equation of this entire line. So what do you need to find the vector equation of a line? You need a point. Do we have a point? Well, we can get it, right? The point lives on the blue curve. And do we have the direction of the line? Yes, what is it? Yeah, it's this vector, right? Understand? Okay, so let's grab that real quick. For the line, I need a point. How can I get the point? Okay, plug in pi over 2 into the original vector function. So let's plug that in. The original one was t, so pi over 2 times sine pi over 2. And then t times cosine pi over 2. And that's the vector, what? Pi over 2, 0. Right? Sine of pi over 2 is 1. So you get pi over 2. Cosine of pi over 2 is 0, so that kills it off. So that's where we live, right? That's actually the blue vector. So this is our R naught, isn't it? That's our R naught for our line. And then now we need the direction vector. But that's exactly what? The derivative, right, of R, at pi over 2, which is the vector 1, was it? Yeah, 1 negative pi over 2. Yes? So now we're ready to write down the vector equation of the tangent line. It will be, and I should not use R of t, should I? Because R of t is already defined in this problem. So let's call it something else. How about, and we're not going to use t because we're going to use t in a little while for tangent. Let me just call it S of t. S of t is a new vector equation. It's our tangent line at the point pi over 2. It is pi over 2 plus t minus pi over 2t. That's this vector plus t times this vector. Agreed? Any questions? Sure? We're good? How about this? Look at this. Look at the vector, the tangent vector right there. Could we do that in Cal 1? It would be an undefined, right? Because back in Cal 1, our tangent line, right? The derivative of our function gave us the slope of the tangent line. And in Cal 1, vertical lines have undefined slopes, so we weren't able to do that, right? But for us here, there's no problem here because the derivative for us is a vector, and pointing straight up, that's okay. You can have vector point straight up. You see how we don't run into that issue here? Also, I'll kind of point something else out to you. Back in Cal 1, if we wanted to find the equation of a line that's tangent to a curve, do you remember you would do something like y minus y naught equals, this would be the derivative at x naught, and then x minus x naught. This would be, that's basically your slope of your tangent line. So this is the slope. This is the slope of your tangent line, and then this is how you come up with the equation. I don't know if that rings a bell, but this right here, in today now, this part right here is really just that vector, that r prime. But it's not, of course, we don't use this equation anymore because we're doing vector equation of a line instead of the generic equation from college algebra. But I just want you to see that that slope still came from a derivative. All right, next thing. Unit tangent vectors. So if r prime of t is a vector function, then r prime of t is a vector. So we can always find, if someone gives you a vector, a non-zero vector, you can always find a vector in the same direction that is unit. What does it mean to be unit? What's a unit vector? The length is 1, right? So this is called the unit tangent vector, and here's what it is. Does this make sense that this formula would be what it is? Capital T of t, right now for us, what this means is the unit tangent vector. And what it is it's our tangent vector divided by its own length. And that's always how we've made a vector have length 1. We just divided it by its own length. We scaled it by its own length. So there's really nothing new here. Here's the same picture we just had. And what you can see, let me slow this down a little bit. What you can see is the red vector is our derivative vector, right? And then always pointing in the same direction as that red one is this one. It's kind of hard to see. It's purple, but the purple one, but it's maintaining unit length the whole time. And the reason why is because later on, we don't need the length of the vector. And for certain applications, we won't need to know how long that vector is. We just need more of the direction. So we just look at its capital T instead. So what would capital T at pi over 2 be for this one? So that's the same problem we just did, right? Same problem we just did? So r of t was t sine t, t cosine t. We found our derivative to be sine t plus t cosine t, and then it was cosine t minus t sine t. And what we want is capital T of t, right? We want capital T of t. But didn't I tell you at pi over 2? I said, right? That's what I asked. What's capital T of pi over 2? So all I need to do is find the derivative at pi over 2, right? And divide it by its own length at pi over 2. So t pi over 2 will be r prime pi over 2 divided by its own length. What was the derivative again? The derivative at pi over 2? What did we get? 1 negative pi over 2. We want to divide that by what? Square root of 1 squared plus negative pi over 2. So pi squared over 4. And you could just rewrite this as a vector. 1 over square root 1 plus pi squared over 4, and then negative pi over 2 over square root 1 plus pi squared over 4. All I did there is just put this scalar inside here, divided each of these components by that, right? That would be the easiest way to do this problem, right? Just plug in pi over 2 and evaluate, and we're done. But what if you were asked to find t of t, capital T of t, but not at a specific point, at a specific point in time? Wouldn't you have to then take this vector and divide it by its own magnitude? And wouldn't the magnitude of that suck to have to get that? Right? It would be the square root of this squared plus this squared. So let me try it. Why am I trying it? Because perhaps you're going to see more of this later. So we just got to make sure we're comfortable with this. Square root of what? Sine t plus t cosine t squared plus cosine t minus t sine t squared. Do you agree that that's the magnitude? Why is it that I'm thinking maybe this won't be so bad? Yeah, but because of the sum, you can't do each one. Because I do have Pythagorean identity, right? Sine squared t plus cosine squared t will be 1. And I'm pretty sure I'm going to get some of that to happen in here. So let me first square this one here. So this equals square root. When you square that, I'm not going to show the work, you should get sine squared t plus 2t cosine 2t sine t cosine t plus what? T squared cosine squared t. Good. Okay, so that's what you would get if you squared this. That means FOIL it all out, collect like terms. You should get this, right? And then what about this one over here? Cosine squared t minus t sine t cosine. I'm just rearranging things, but that is correct. And then the last term would be plus t squared sine squared t. Yes? Do you see anything good? This one and this one are gone, right? Yeah. This one and this one are 1. What about this one and this one? You pull out a t squared out of that, right? Right. This one right here, you can pull t squared out, and you have sine squared t plus cosine squared t. Do y'all agree? That's what would happen if I put these two together. Pull a t squared out, and then this right here is a 1, isn't it? Y'all following this algebra here? Okay. And then this became a 1. So all you're left with is what? Square root of 1 plus t squared. That ain't so bad. In fact, when we plugged in pi over 2 a second ago, right? When we plugged in pi over 2, our length, didn't we get square root of 1 plus pi squared over 4? Which is what we would get if we use this formula. So you see, I'm just trying to get you to not be so intimidated by the idea of finding a magnitude of something like this, because this will happen some of the time. Not guaranteed to happen all the time, but at least know that you can take a swing at it and good things might happen. All right. So here's a problem where I'm asking to find the vector equation of the line tangent to this curve at this point. What's the difference between this problem and the previous problem? The one that we did a few ago. What is it? We're in 3D, right? We're in 3D now? For the vector equation of the line, I need r prime, don't I? Yes? So let's go ahead and get r prime now. So my r of t, there's something very subtle in this problem that I want to make sure everyone understands. I'm not there yet. I'll get to it in a second, but here's our vector function. We want to find its derivative, right? Derivative pretty straightforward. Negative 2 sine t, cosine t, and 1, right? Well, I need to find the vector equation of the line that's tangent to this curve at a certain point. So I'm trying to find this s of t, right? That's what we had earlier, s of t, which I'll say we need s naught plus tv, s naught, s naught. Okay, right? That's what we need. So do I have s naught? Do I have a point on the line? Do I have a point on the tangent line? Well, I was given something in the problem, right? What was I given? At the point, right? So I said at the point 0, 1, pi over 2, right? So I actually have s naught, don't I? This is 0, 1, pi over 2. Plus t times, now I need v, right? How are you going to get v? V is the direction, right? So v is the derivative, correct? But where? This is the subtle part. But where? In the previous problem, where were we working? Where were we finding that tangent line? What was it that I gave you? I gave you a value of t, right? I gave you t was pi over 2. I don't give you a value of t here, do I? To figure out where that's happening? So how can you get t? Yes, this point has to live on this curve, right? This point has to live on the curve, which means there's some value of t that I plug in here, here, and here. Same value for all of them. That spits out that point. Can you tell by looking? It's kind of obvious, isn't it? Is it obvious or not? Just look at your z. It's pi over 2, right? T is exactly pi over 2. If you come right here, what's sine of pi over 2? 1. And then what's 2 times cosine of pi over 2? 0. So do you agree that t equals pi over 2 works? So you see how we had to go back and recover what t was? That's important, all right? That's going to happen again certain times in this class where I give you a point, curve goes through it, you have to figure out what point of time it actually goes through. So to get v here, to get this v, I actually need to know what the derivative is at pi over 2. The derivative at pi over 2, which for us would be what? Negative 2, 0, 1. And that means my direction vector down here is negative 2, 0, 1. Is this good enough? Is that the vector equation of a line? Okay. Any questions here? This was the curve. This was the curve. That's from the top, looking down on it. All right, second derivative. Of course, just as you'd think, just take derivative of the derivative. That's second derivative. But we use the second derivative to define something that we don't have in Cal 1. It's called smoothness. A vector function r of t, which is given on some interval I, is called smooth if the derivative is continuous. That means the derivative exists. And if the derivative is not 0 on that interval, except possibly at the endpoints. So when your derivative is 0, your function is not smooth. All right? If your derivative is 0 somewhere, except at the endpoints, your derivative is not considered to be smooth. And your function is not considered to be smooth. So here is a function, okay? Is r of t equals cosine squared t, and then t to the fourth, a smooth curve on all real numbers. Let me show you the graph, and then we'll compute. Here's the graph. So time's going by. Notice the tangent vector, right? Notice tangent vector, and then this. Is this a smooth curve? Well, I have to check. Is the derivative ever 0? Is it ever 0? Well, what is our derivative? Well, what's our vector function? It was cosine squared t, t to the fourth. Here's the thing. I showed you that picture, right? Be careful. When I said is the derivative ever 0? Right? When I said that, is the derivative ever 0? We know in Cal 1, derivative 0 means horizontal line, right? Does derivative 0 now mean horizontal line? Because derivative is a vector, right? Derivative being 0 means that we get the 0 vector. The 0 vector doesn't have a direction. So I don't want you to look at this and say, oh, because this red vector here, which is our tangent, is flattening out, it's 0. That's not the connection I want you to make. It's just, is the derivative 0 or not? Understand what I'm saying or not? Okay, so let's take our derivative. We're going to have to do some chain rule here. I already cleaned it up. That's your derivative cosine squared t. That's your derivative of t to the 4th. And the question is this ever 0? Is there a t that makes that 0 or not? Can anyone see? 0 vector, sorry, that should be vector up there. Is that ever 0? Well, the only way to get the 0 vector is for both components to be 0, right? What's the only value of t that I could have to make the second component 0? 0 itself, right? So let's see, at t equals 0, what do we get? Well, this goes, what? 0 and then 0. So yeah, at 0, t equals 0, we get the 0 vector. So when we go back and look at this, again, playing this slowly, what's happening, okay, it's not the fact that the vector flattened out, it's actually that the vector did what? Look at the 0 vector should have a length of what? 0. So look at the length of this vector. It goes to 0 and then gets big again. Anytime the derivative is 0, that means that the tangent vector goes to 0. A function in 2 or 3-dimensional space is called smooth if that never happens. If it happens, it's not smooth. Go ahead. For smooth, it's first derivative. The first derivative can't be 0. What was the other? I thought I heard someone else say something. No? This graph is not smooth. Well, this function is not smooth at 0, right? Everywhere else it's smooth. Like if you were to just look at this graph, this is our time over here. So if you look at the time, what's happening before I get to 0, any point before 0, I'm okay on that interval. But on the entire real numbers, it's not smooth because it's undefined at one point, or the derivative is 0 at one point. Go back to the definition of smooth. A vector function given on some interval is called smooth on that interval if the derivative is continuous and the derivative is never 0 except at the endpoints. Except at that place, yes. At t equals 0. Smooth is not really a concept that we're going to get into too much, but it is something. It is defined that way, so got to introduce you to it. All right, so some of the rules for derivatives that extend from what we learned in Cal 1 to Cal 2, to Cal 3. If you have 2 vector functions and you're adding them and you want to take the derivative, you just do derivative of each one. If you have a constant in front of a vector function, you can take the constant out and then take the derivative. This is all stuff that you've seen in Cal 1. This one's kind of interesting. If you have a vector function being multiplied by, what kind of function is this? A scalar function. And you want to take the derivative, then this is the derivative. Does that look familiar? That's product rule. What about this one? The derivative of a vector function dotted with another vector function is this. What is that? Product rule again, but your product this time is a dot product, right? Not your traditional multiplication. And then if you want to take the derivative of a cross product of 2 vector functions, it again is like product rule, except your product is a cross product instead of a standard multiplication. Now all of these are properties. These are things that I'm not going to show you. You could show these yourself, by taking u of t, calling it like u1, u2, u3, taking that vector, then v1, v2, v3, and then you could cross them, take their derivative, and figure out what that is, and then you could come over here and confirm that it matches up with this. So take derivative, then cross, take derivative, then cross, and then put those together. The left and right-hand sides should match. But I'm not going to verify it. And then last one, if you have a vector function evaluated at a scalar function, then the derivative of that is, what rule is that? Chain rule. You take the derivative of the vector function, you do not mess with the scalar inside, then you multiply times the derivative of the scalar. Well, we're applying a lot of, what we're doing is we're saying, we've introduced this new like vector function idea, and we're saying, well, how much that we learned with scalar functions also extends here. And it turns out that most of the properties extend naturally right to this. We have to keep in mind we have two new definitions of products here. So product rule didn't have to apply the same way, but it just turns out it does. Sometimes math is kind of elegant in the fact that it does what you think it's supposed to do, but then there's other times where it doesn't. Okay, this one. Show, where am I? Lost my spot here. Show that if r of t is cosine t sine t, what does that draw? Unit circle, right? Unit circle. Then r of t is orthogonal to r prime of t for all t. It's a circle, right? If you're traveling along this circle and you imagine that tangent vector, it's saying to show that the vector function is orthogonal to its derivative. Here's the picture. The key here is you have to remember that when we defined a vector function, we said that it creates vectors, right? From the origin to somewhere. And that place where it goes to is the point on the curve. So you have vector, 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 and it draws the circle out, right? This is trying to get us to show that the vector that's created, r of t, is always orthogonal to its derivative. It makes sense on a circle that it would be that way, right? But show it, prove it. You can't prove it with the geometric proof. You have to prove it algebraically. So how do I show that something is orthogonal to something? Show that the dot product is what? 0. So I want to show, WTS, I want to show that r of t dotted with what? R prime of t is what? 0. Right? The number 0, not the 0 vector. That's what I want to show. Everyone understand why I want to show that? If I show that, that means they're orthogonal to each other. So what was r of t? Cosine t sine t? And I want to dot that with its derivative. What's the derivative of r of t? Negative sine t cosine t. All right? Now, dot them, and you multiply this times this, right? Which is negative sine t cosine t. And then you add to that, because it's a dot product, this times this, which is cosine t sine t, or sine t cosine t. And when you put those two together, they cancel, and you get 0. Regardless of t, right? Regardless of t. You dot r with its derivative, you always get 0. That means that it's always orthogonal to itself. The tangent is always orthogonal to the curve. No. The tangent vector is always orthogonal to the vector function. So the vector coming out from the origin to the curve. Does that seem pretty natural? Yes? Questions at all? The next example, question? For all t, right? Because t didn't matter here. No, not for all functions. For this particular one, it does. You could show for others it doesn't. But if you draw a circle then your tangent vector is always going to be orthogonal. Look at this next example. This is one of my favorite examples in this chapter, because the way we're going to show it is so unorthodox, so unnatural. It gives you a glimpse into the world of the way math people think, all right, and the way they go about proving things are true. Show that if the magnitude of your vector function, that's the distance, right? The magnitude of a vector is its length. Show that if the distance is constant, then R of t is orthogonal to its derivative for all t. Everyone understand what's being asked? This is constant, right? Doesn't that mean that when I'm drawing the curve, I always have to stay the same distance from the origin? Does that mean it has to be a circle? Does it have to be a circle, though? No. I mean, we're in two-dimensional space or three-dimensional space here. It doesn't matter. So imagine, yes, you in three-dimensional space, you'd have to stay on a sphere, right? To stay the same distance, but you wouldn't have to draw anything in particular. You could be, just imagine an ant crawling along a sphere, and that path is always the same distance from the origin, right? But that's the path it's walking is in no way, shape, or form some standard shape. You know, it's not like a circle in two-dimensional space. So this condition seems pretty strong, but you can think of a lot of different paths in three-dimensional space that do that. We're trying to show that no matter what, the tangent vector is always orthogonal to the vector pointing out to it. So the approach here, I think, like I said, I'm going to show it to you, and it's not something that you would normally have come across, I don't think. So what we want to show, right, we want to show that the original vector function dotted with its derivative is 0. That's the same thing we wanted to show last time, right? But see, I didn't give you a vector function, did I? Like, you don't have anything to take the derivative of. So the only thing you know is what? What's given? The magnitude of the original vector function is a constant. All right, so check this out. As a math person, right, I'm not claiming myself, I'm just saying math, the way the mathematicians work with things like this is they go and they try and figure out anything they can that'll help them get to this, all right? So I want to see if you recall this. This came from earlier. That if you take R and you dot it with itself, what would you get? It might help if you looked back in your notes and you said when we took a vector u and dotted it with itself, do you remember what it gave you? The magnitude of u squared, right? It gave us the magnitude of u squared. And see, the magnitude of u is here now, right? So if I say R dotted with itself gives us that magnitude squared, right? Then I have some relationship between a dot product and a magnitude. Do you see that? That's the first connection as a math person would make. Okay, like I know this much is true, right? I know that much is true. I'm going to take this out of here. All right. But somewhere I need the derivative in here, don't I? I need the derivative. So where can I find a way of getting my derivative in my original function in there and that magnitude in there and the dot product? How the hell do I do it? So someone sits there and suffers with it for who knows how long and finally realizes, look, why don't I take the derivative with respect to t of r of t dotted with itself. Well, we just talked about properties, right? What is the derivative of something dotted with its, well, dotted with anything? It's product rule, isn't it? But I have r of t here and r of t here, so this is just going to be r prime t dot r prime, r prime t dot r of t plus r prime t dot r of t again. Y'all follow? So this becomes r prime t dot r of t plus r prime t dot r of t. How many of those do we have there? Two of them, right? So 2 r prime t dot r of t equals, what's this? We said that this was, this right here was this, right? But what's the magnitude of our vector? C, right? C squared. So this is c squared, isn't it, right here? Just this part right here is c squared. And what's the derivative of a constant squared? 0, right? Do y'all follow that? This, algebraically, this is what this means, right? Using properties of what product rule is over dot products, this is what we get. But at the end of the day, this is a constant. That was given to us in the problem, right? That's a constant square. And the derivative of any constant should be 0. Well, divide both sides by 2, and what do you get? R of t dotted with r prime of t is 0, which is what I wanted to show. That kind of makes sense? This is weird, but I mean, how would you ever come up with that way of, I mean, how would you ever know, given this problem, that I should take r and dot it with itself and take its derivative? Like, that's just not a very natural thing that you would just automatically snap in your head to do, right? And that happens a lot with math in the field of math, is that you have to find unique ways to get to places. All right, so we're done here, right? So we usually write like QED, or we do a little box like this, and that means we've shown what we wanted. This is in no way a nice, elegant putting my ideas down clearly, all right? I would totally want to rewrite this a proper way now, but this was just a kind of like, I was thinking through it, trying to get you to see it. So I won't ask you anything like that on a test. Okay, some of the applications of derivatives. We got a ways to go, don't we? Okay, so this, I'm not going to go through all of this because there's a lot here, okay? I'm just going to show you the picture of what's happening. What I have are two vector functions, R1 and R2, all right? They both draw the exact same curve. They draw the exact same curve. If I plug in 0, 0, if I plug in 0 to the first one, I'm at 0, 0, right? Plug in 0 over here, I'm at 0, 0. If I plug in 1 over here, I'm at 1, 1. I plug in 1 over here, I'm at 1, 1, right? What happens if I plug 2 into the first one? Where am I at? I'm at 2, 4. If I plug 2 over here, where am I at? 4, 8. So I'm not at the same place, am I? But if I take, how about if I, instead of plugging, well, plug 2 in here, you got 2, 4, right? What if I plug square root of 2 in over here? I would get square root of 2 squared, which is 2, and then square root of 2 to the 4th, which would be 4. So there is a value of t I could plug in here that would still give me 2, 4, wouldn't it? It's just not the same as the t value here. What I'm trying to get you to see is that although they draw the same curve, they don't draw them at the same rate. So if we were to sit here and say, okay, ready, on your mark, set, go, we're going to start the clock. Okay, do y'all see the points? T is going. Now what's happened? That one's already off, right? Now here, this one starts together, and then all of a sudden that one's gone, right? This one's still drawing. But they draw the same curve. See, T is do y'all see that T is the same for both? So we want to find a way of somehow connecting the rate at which that's happening. We need to somehow quantify that. And so let's take a look at the derivatives. Look at the derivatives there. Now, there are two different points on the graph, right now. But look at how much longer this one is here than this one is. And let me just move it forward in time a little bit. Actually, let me move it backwards. Okay, this one right here, the x value, the t value is 1, right? So I'm at 1, 1, and then there's the length of the vector there coming out, right? When I'm at 1, 1 here, right, 1, 1, look at this. That doesn't look right. Let me do this. This will probably be better. Here we go. Look at what's happening. Look at the length of the vector here compared to the length of the vector here. And then I have a couple more comparisons. What I'm doing is I'm bringing the R2 over there, I'm bringing them over here so you can see them compared. So you can see the black one is R1, the purple one's R2. Here's R1, here's R2. You see how much longer the R2 is? So the tangent vector, the derivative, the length of it's longer. That somehow represents the speed at which I'm moving. And that's kind of the crux of what this is all about. Okay? If R of t is a vector function which represents the path of an object through space, then we call it a position function. Tells you where something is. V of t, this is all Cal 1, but there's some subtle differences. V of t is now going to be the derivative of r. That's our velocity function. It gives us the velocity. Okay, but velocity, the velocity function is a vector function, so velocity for us is a vector. Now, the magnitude of the derivative, or the magnitude of the velocity function, is the speed of the particle. And then, of course, a of t, which would be the second derivative, is called the acceleration function. So, the larger the magnitude of the derivative, the faster the particle is moving at that point in time. So start with r of t, it's a vector function, right? Take its derivative, velocity function, but it's still a vector function. Take derivative again, it's acceleration function. If someone asks you for the speed of a particle, do they want the velocity function? No, they want the magnitude of it, right? So anyone who's taken physics knows that there's a difference between speed and velocity, right? Velocity is a vector, speed is its length. That's all it is. Velocity is a vector, speed is the length of that vector. In Cal 1, velocity and speed meant the same thing in Cal 1. It was the slope of the tangent line. It didn't matter any other way. There wasn't any other way to look at it because we weren't looking at it in terms of vectors. I hope that makes sense. All right, let me see if that's the right. I was going to do some problems in class. Let me see. I don't even know if this is the right page. 586. How are we doing on time? No, it's actually page 589. I don't think I'm going to do those, because there's a few more applications we need to get to. right. So now we do some integration. If r of t is a vector function, then if you want to integrate it, find the antiderivative, then you just integrate each of your component functions. Definite integral or indefinite, doesn't matter. Either way, you integrate term by, not term by term, component by component integration. Remember, the answer would be a vector function. For example, what if we were asked to find the antiderivative of r of t in this definite integral from 1 to e? Do that one real quick. So if we want to integrate from 1 to e, the vector function e to the t square root t minus 1 natural log t dt. You just do the integral of each one. So you can do them separately if you want. 1 to e to the t dt. Then do another one, integral 1 to e, t square root t minus 1 dt. Then the next one, integral 1 to e, natural log t dt. Now remember in the previous take-home quiz, I was asking you to do like L'Hopital's rule stuff from Cal 1 you hadn't seen in a while, right? So guess what you're going to get when your take-home quiz this time if you have to find integrals? Cal 2 integrals that you probably haven't done in a while, right? So be prepared for types of integrals you're going to see. I'll hand it out to you in a second. But how about the first one? This one pretty straightforward. Antiderivative e to the t, e to t. Evaluate 1 to e, which gives you what? E to the e minus e. Right, you're just plugging in e here, and then you're plugging in 1, right? Subtracting. How about this one? How are you going to integrate that one? Well, that's the question. How are you going to integrate that one? Integration by parts might work. This one actually probably goes, the cleanest way is to go just to use substitution. And if you do that, we can rewrite this integral as what? If this is u now, if t minus 1 is u, then we have a square root u there, don't we? But what is t? Solve this for t, get u plus 1. And what's dt? Is du, right? Y'all see what I did there? And now these are all powers of u, right? Like you could distribute this through. This becomes u to the 3 halves plus u to the 1/2 integral du. And then you could take it the rest of the way. I'm not going to do it. But that's just to show you that one just went with the basic substitution. So brush off the cobwebs. Antiderivative of natural log t, that's derivative. Other way. T, depending on how often your Cal 2 instructor made you do this, this is one of the ones I told my students, try and memorize, but it's hard, people forget it. It's t natural log t minus t. But you can do this one with integration by parts. I'm not going to do it. All right, I don't have a whole lot of time here. When you integrate something, okay, look, for this one, I give you the derivative and I ask you to go back to the position, right? This is like the velocity, and I'm asking you to go back to position. When you integrate something and it's not a definite integral, you have constants of integration, don't you? You have constants of integration? So what would happen if I integrate this right here? my constant of integration is actually a vector constant. It's a vector. It's a constant, but it's a vector. And then I use this initial condition to figure out what the vector is. Let's do this, because I don't think I have enough time to truly treat that, and I still have Wednesday. I'll just pass out your new quiz, and we'll kind of pick up there. I'll do that example when we return. But I wanted to just take a minute to look at the quiz together. Let's see, 1, 2, 3. I think I only printed out 15 of these. 3, 4, 5, 6, 7, 8, 9. I have an extra there? Let me see. No extra. We missing 1, 2? We need another one? I don't think I have another one. Okay, well, I can email it out too later, but I won't have it till later. All right, so I'm going to look off, I'm going to turn the lights on and just talk through this real quick. Talk about what you can do right now on this. Okay, so number 1A, find the value or values of t where the particle moves along the curve. R of t is blah, 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 has the maximum speed. Yeah, speed we just said is the magnitude of the velocity, right? But you want to find where something is a maximum, right? Where it has the maximum speed, and I give you an interval. Okay, and then ask for what is the maximum speed. I'll get back to that, okay? But I think you're on the right track there, suggesting that derivative, and okay. Number 2, I give you the acceleration vector function, right? I give you 2 pieces of information, and then I ask you to find its distance function. Or no, the distance from the particle to a plane. So I start with the acceleration. From the acceleration, you got to go backwards to velocity. Then you got to go backwards to position. Once you find its position, then you have to figure out exactly at a point in time where it is, and then you have to figure out how far it is from a plane. It's a lot of things together here, but especially the integration. Look at the integration you're going to have to do. Look at the vector function I give you. You have to integrate 1 over t plus 1 squared, or negative 1 over t plus 1. Is that t plus 1? Yeah. The second component function is kind of weird to integrate. Secant cubed t plus tangent squared secant t. And after you integrate that first time, you have to integrate again. So that's going to be a little bit of a problem there, but you'll work with it. And then I would definitely use some identities there, yeah. Number 3, you have a particle. Oh, we haven't talked about arc length yet. And then we haven't done number 4. So you can at least start to entertain number 1 and 2. But let me talk about something on number 1 that people get wrong, all right? There are 2, I won't write on that, I'll write on the board. 2 things from Cal 1 that you need to remember to do number 1 here. And this will also come up later. In Cal 1, one of the fundamental things that we learned was that if somebody gives you a function, f, on a closed interval, AB, that you can find the absolute or global maximum and global minimum. Okay, it's called the closed interval method for finding maximums and minimums. There's a way of doing it. And in problem number 1, I give you something and ask you to find the maximum of it on a closed interval, right? Don't I give you a closed interval there? So when you get to, you're going to basically have to come up with this function f. Once you come up with that function, you need to go back to Cal 1 to find its max. Okay, so there's a Cal 3 part of this problem that you first come up with the function that represents the speed, and then you find out when it's the biggest. you might need help for that. Now, the other thing to remember you probably won't need for this test, but will need later, is that if you have a function and it's not on a closed interval, then we can find local maximums and local minimums of a function by applying calculus to it. There's several ways, but one of them was called the second derivative test, where you figure out where local maxes and mins occur. So you need to remember those two methods for finding highest and lowest values of a function. Closed interval method, open interval method. You need that for number one. All right? I've kept you over time. Everyone have a good rest of your day. Was there a homework assignment at the end? Yeah, there's a homework. 568. Make sure it's the right page. Whoa, that's way off on the page. I think it's 589.